So in another video, we talked about the basic idea behind solid solution. Here we're going to talk about different types, and we're going to start with substitutional solid solution. We'll use olivine as an example. We have the mineral forsterite, Mg2SiO4, and we might ask, what else can we substitute for magnesium? So here is the mineral forsterite. And those of you who are experienced in mineralogy maybe are already aware that we can substitute iron and we can make Fe2SiO4, and that gives us the mineral phthalate. We can have a single phase, a single solid substance that we would call olivine, and it would be comprised of two components, a magnesium-rich component that we would call forsterite and an iron-rich component that we would call phthalate. And there are the formula of the respective materials. But you might ask, what else could we put into here? Could we add calcium or nickel or strontium or other kinds of 2+ cations? Well, it's not just the charge that matters. Anything that has a 2+ charge will certainly satisfy what we call the stoichiometry, the balance of cations that fit here in a 6-fold coordination site. We'll put a Roman numeral 6 here, along with silica and oxygen in these atomic proportions. But it's also the size that matters, and there's a general rule that if the radii of two cations, let's say magnesium and iron here specifically is in the 2+ state, if these fellows are within, let's say, about 10 or 15% of one another, we should have complete solid solution. So we can write this as kind of a 15% rule. If we're to the left of this, we have less than 15% difference in the radii, then we would have complete solid solution. That is, we can take as many magnesium or iron atoms as we like and mix them and match in any proportion that we like, from 100% magnesium to 100% iron or anything in between. And all those substitutions would be allowed. But if we get greater than 15%, then we would have limited substitution. Then if we start putting too large of a cation in, it starts distorting the structure and it limits its stability. And then there's finally another limit, and this is approximately 30%, where beyond that we would have very limited at best, or more likely no substitution at all. So we would have no solid solution or limited solid solution. We'll just write SS for solid solution, or complete. So we can compare the radii, and we'll do that in this next slide. So we'll clear the chalkboard. Let's take a look at the radius of magnesium, 2+, and if it is in 6-fold coordination, it would have an atomic radius of about 0.72 angstroms. If we take iron 2+, also in 6-fold coordination, it would have a radius of 0.78. Let's take magnesium as the reference. So we'll take 0.72 minus 0.78 and divide that by 0.72. Taking magnesium as the reference, it's going to be down here at the bottom in the numerator. Let me put it here in that first slot as well. And so we would get a value of minus 0.0833. The 3's repeat, we'll just put a bar over it. So that is equal to 8.3%, well, a negative 8.3%. So the radius of magnesium is 8.3% smaller than iron, but that is less than our critical value of 15%, where we only care about the absolute value here, not the negative sign. And so since it's our less than our 15% value, we should expect complete solid solution. And those of you who are familiar with the olivine series already know that forsterite and phthalate can mix with each other in any proportions. Let's take something different. How about potassium with a 1+ charge, and compare that to sodium that also has a 1+ charge? We could think about these substituting in a feldspar. Let's write that a little more neatly. That's a 1+. And let's say we're going to put them into 8-fold coordination with oxygen. So for potassium, it would have a radius of 1.51 angstroms, and sodium would be 1.18. And so if we take the difference of those, we'll just take the positive difference, 1.51 minus 1.18 divided by 1.51. So here potassium is our reference. we would get 0.218, which is equal to 21.8%. We can reverse the comparison and put 1.18 at the bottom. We would still get a value that is greater than 15%. And so this means that we would not have complete solid solution. Instead, we would have limited solid solution. So we can substitute potassium and sodium for one another, but not completely. Notice, by the way, that the only thing that matters here is the charge and the coordination number. There's nothing specific to the minerals that we are choosing. If we have any kind of mineral, be it a feldspar or a feldspathoid or anything else, if we have eightfold coordination, then this kind of analysis applies. Same thing for our comparison of magnesium and iron. Let's look at one more case. Now we asked whether or not we could make a strontium olivine. Could we put strontium in for magnesium and have an olivine that looks something like this? Is this even possible? Well, the radius of strontium, if it is in sixfold coordination and the 2+ state, would be about 1.18 angstroms. Interestingly enough, identical to sodium in the prior case. And then we have the radius of magnesium, always 2+, again in sixfold coordination for olivine, and again at 0.72 angstroms. We'll take the difference, 0.72 minus 1.18 divided by 0.72. We're going to use magnesium as our reference because we know that the Mg2 SiO4 case exists. So we're wondering if we could put in strontium here, and we get a value of 0.639. So that is 63.9%. Well, that is supposed to be a percent sign. And 63.9% is greater than that critical value of 30%. So we would estimate that, or guess that there is going to be no solid solution between the strontium component and magnesium components. The olivine crystals that you might pick up from a lava flow somewhere might have lots of iron, at least iron 2+, but they shouldn't have any strontium. Or if they do, it's just going to be in very, very trace amounts. They might form a different kind of solid solution, maybe an interstitial solution. This is something we'll look at in another video. But for the basic idea of substituting one cation for another, can we put iron in for magnesium, or potassium in for sodium, or strontium in for, let's say, iron 2+ or magnesium? We can use that basic 15 and 30% rules to make some estimates about what will fit and what will not.